It's easy to forget just how fast things changed. 2 years ago, when we talked about distant galaxies, most of what we said came with a giant asterisk. We thought we saw the first stars forming. We believed we had an idea of what early galaxies looked like. And when it came to alien planets, we were basically guessing, tracing shadows and hoping for the best. Then James Webb opened its eyes and suddenly the asterisk started disappearing. We weren't just detecting planets anymore, we were finding actual signs of what might be in their atmospheres. We weren't squinting at blurry dots from 13 billion years ago. We were looking at fully formed galaxies that, according to everything we thought we knew, shouldn't have even existed yet. And that was just in the first few months. But to really understand what Webb has given us, we need to go back further than the launch. We need to understand what came before, what made this telescope possible, and why it almost didn't happen at all. Because the story of James Webb isn't just about what it found, it's about 3 decades of persistence, failure, redesign, and the kind of stubborn optimism that refuses to accept that some questions might be unanswerable. Back in 1989, when the idea first emerged, no one called it James Webb. They called it the Next Generation Space Telescope, which tells you everything you need to know about how ambitious and vague the concept was. The only real requirement was simple on paper, but impossible in practice. Build something that could see the very first stars. Not hints of them, not models. The actual light from the moment the universe first learned how to shine. Hubble was still years away from launch at that point, and already NASA was thinking about its successor. That's how long these projects take. That's how far ahead you have to think when you're building something that has to work perfectly 1,000,000 miles from Earth with no second chances. The early designs were wild. Mirrors 8 meters across. Mirrors 10 meters. Mirrors that would unfold like origami in space because there was no rocket big enough to carry them fully assembled. And the budget? Well, that kept changing. First it was $500 million, then $1 billion, then $3 billion. And every time the price went up, Congress asked the same question. Why? Why do we need this? What's wrong with Hubble? And the answer was always the same. Hubble can't see far enough. It can't see cold things. It can't see through dust. It works in visible light, and that's incredible, but the early universe doesn't speak in visible light anymore. By the time that ancient light reaches us, it's been stretched, redshifted, pulled by the expansion of space itself into infrared wavelengths that Hubble was never designed to detect. So if you wanted to see the first galaxies, the first stars, the moments when the universe stopped being dark and started being interesting, you needed infrared, you needed cold, you needed a telescope that could operate at temperatures so low that even the faintest heat from its own instruments wouldn't drown out the signal. That meant putting it far from Earth, far from the sun, in a place where it could stay perpetually shaded, cooled by the vacuum of space itself. That place is called L2, the second Lagrange point, about 1,000,000 miles from Earth in the opposite direction from the Sunday. It's not an orbit around Earth, it's an orbit around the Sun that matches Earth's year, keeping the telescope in a fixed position relative to us, always with Earth, Moon and Sun on one side and the rest of the universe on the other. And that's where Webb would need to live for the next decade or two, completely on its own, with no possibility of repair missions, no astronauts to fix mistakes, no do-overs. The design kept evolving. By 2002, the telescope had a name, James Webb, after NASA's second administrator, the man who ran the agency during the Apollo era. Some scientists didn't love that choice. They wanted something more poetic, more universal, but the name stuck. By then, the mirror design had been finalized, 18 hexagonal segments made of beryllium, coated in gold, arranged in a honeycomb pattern that would unfold in space to create a collecting area of 6.5 meters. That's more than double Hubble's diameter and nearly 7 times its collecting area. And gold wasn't just for looks. Gold reflects infrared light better than almost anything else. So every segment, every surface that would see starlight, had to be coated in a layer of gold so thin you could see through it if you held it up to a window. But spread across the entire mirror, it was just enough to catch the faintest whispers of heat from the edge of time. Then there was the sun shield. If the mirror is the eye of the telescope, the sun shield is its eyelid, the thing that keeps it from being blinded by the sun's glare. And it's not a simple sheet of metal. It's 5 layers of Kapton film, each one the size of a tennis court, separated by gaps that create insulation pockets, keeping the hot side at over 200 degrees Fahrenheit, while the cold side, where the instruments live, stays near -400 degrees. That temperature difference is what makes Webb work. Without it, the telescope's own heat would overwhelm the faint signals it's trying to detect. It would be like trying to see stars at noon. The sun shield had to deploy perfectly. All 5 layers had to separate, stretch, and tension without tearing, without snagging, without a single bolt failing to release. And there were hundreds of them, hundreds of single points of failure, each one capable of ending the mission before it even started. Testing took years. They built prototypes, subjected them to temperature swings, vibration tests, acoustic tests that simulated the violence of launch. They folded and unfolded the sun shield over and over, looking for weaknesses, points of stress. And they found them. Over and over, they found problems. Tears in the material, fasteners that didn't release, mechanisms that jammed. And every time they found a problem, they had to stop, redesign, retest. The launch date slipped, and 2007 became 2011. 2011 became 2014. 2014 became 2018. And with every delay, the budget grew. By 2010, the project was nearly cancelled. Congress was losing patience. The telescope had become a punchline, a symbol of government waste, an astronomy project that cost more than some countries' GDP. But NASA fought for it. The scientific community fought for it. Because by then, it wasn't just a telescope anymore. It was the future of astronomy. Entire careers were being planned around it. Surveys, proposals, instruments, theories, all waiting for Webb to launch so they could finally test their ideas against reality. And then, slowly, the pieces started coming together. The mirror segments were polished to a precision measured in nanometers, each one shaped so perfectly that if you scaled one up to the size of the United States, the biggest imperfection would be less than an inch tall. Think about that for a moment. These mirrors, each one about the size of a coffee table, were polished so smoothly that light waves, traveling at 186,000 miles per second, would bounce off the surface without detecting any bumps or irregularities larger than a tiny fraction of their wavelength. That level of precision required years of work, using computer-controlled polishing machines that could remove material, one atom at a time if necessary, constantly measuring and remeasuring, comparing the actual surface to the target shape, making microscopic adjustments. And each segment had to match not just an ideal shape, but a specific shape designed to work in concert with the other 17 segments when they were all aligned in space. The instruments were integrated, 4 of them, each designed to do something different. NIRC, the near-infrared camera for capturing images. NIR-SPEC, the spectrograph for analyzing light. MIRI, the mid-infrared instrument for seeing even colder, even older objects. And NIRIS, the Canadian-built imager and slitless spectrograph, designed for exoplanet work and wide-field surveys. Each one represented years of development, international collaboration, cutting-edge technology, and all of them had to work together, perfectly, in an environment no one could fully test on Earth. NIRCam was built by a team at the University of Arizona, led by Marcia Rique, who had been working on infrared detectors for decades. The camera uses mercury-cadmium telluride detectors, materials that are sensitive to infrared light, but have to be cooled to incredibly low temperatures to work properly. At room temperature, the thermal noise from the detector itself would swamp any signal from distant galaxies. But at -400 degrees, the detectors are quiet enough to register individual photons arriving from objects billions of light-years away. NIRSPEC, built by the European Space Agency with contributions from NASA, was even more complex. It's a spectrograph, which means it doesn't just capture images, It splits light into its component wavelengths, creating a spectrum that reveals what the object is made of, how fast it's moving, how hot it is. But unlike most spectrographs, which can only study one object at a time, NIRSpec uses a technology called microshutters. These are tiny metal shutters, each one about the width of a human hair, arranged in a grid. By opening and closing individual shutters, NIRSpec can study up to 100 objects simultaneously, collecting spectra from dozens of galaxies in a single observation. That's crucial for deep field surveys, where a single image might contain hundreds or thousands of galaxies, and you want to study as many as possible without having to point the telescope at each one individually. MIRI, the mid-infrared instrument, was perhaps the most challenging to build. It operates at even longer wavelengths than the other instruments, looking at light that's been stretched even more by cosmic expansion, light from objects that are colder and more distant. But mid-infrared light is also harder to detect because warm objects emit it. Even at the cold side of Webb's sunshield, at -400 degrees, the telescope's own instruments would glow brightly in mid-infrared, overwhelming any signals from space. So MIRI needed its own cooling system, a cryocooler that uses helium gas to carry heat away from the detectors, bringing them down to -447 degrees Fahrenheit, just a few degrees above absolute zero. That cryocooler was a marvel of engineering, a mechanical system with moving parts that had to work reliably in the vacuum of space for years without maintenance. And it worked. MIRI has been operating flawlessly, delivering observations of dust clouds, protoplanetary disks, and distant galaxies that would be invisible to any other instrument. NIRISS, the Canadian contribution, brought its own innovations. It was designed specifically for studying exoplanet atmospheres, using a technique called single-object slitless spectroscopy. When a planet transits in front of its star, NIRISS can capture the starlight filtering through the planet's atmosphere and spread it into a spectrum, revealing absorption lines from molecules like water vapor, carbon dioxide, and methane. It can also do wide-field imaging, capturing large areas of sky in a single exposure, making it useful for surveys and for studying extended objects like nearby galaxies. Canada's investment in NIRISS, part of their contribution to the Webb partnership, guaranteed Canadian astronomers a share of observing time on the telescope, ensuring that the global community would benefit from the mission. By 2016, the telescope was finally taking shape. Fully assembled for the first time, it looked like a giant golden flower folded up inside a clean room, surrounded by engineers in bunny suits. Every surface protected, every connection checked and rechecked. But there was still more testing to do. They put the entire telescope in a thermal vacuum chamber, the largest ever built, to simulate the cold of space. This chamber, located at NASA's Johnson Space Center in Houston, was big enough to hold the entire observatory, and it could be cooled down to the temperatures Webb would experience at L2. The tests took months. Engineers monitored every sensor, every actuator, every electrical connection, making sure everything worked at the extreme cold. They discovered issues, of course. Some materials contracted more than expected. Some electronics behaved differently at low temperatures. Each problem was documented, analyzed, fixed. They bombarded the telescope with sound, shaking it with the noise of a rocket launch. This acoustic testing, conducted at NASA's Goddard Space Flight Center, used massive speakers to create sound levels of over 140 decibels, louder than a jet engine. The test simulated the intense vibrations and pressure waves that the telescope would experience during the first few minutes of flight as the Ariane 5 rocket accelerated through the atmosphere. Every component, every fastener, every solder joint had to survive that shaking without breaking, without shifting, without failing, and they did. The telescope survived the acoustic tests, proving it could handle the violence of launch. They tested the deployment sequence hundreds of times in simulation, then dozens of times with the real hardware. This was perhaps the most nerve-wracking part, because so much of the mission depended on deployment working perfectly. In space, there would be no second chances. If a motor didn't fire, if a cable snagged, if a panel didn't unfold, the mission would fail. So the engineers practiced, over and over in clean rooms on Earth, deploying the sunshield layers, unfolding the mirror segments, extending the secondary mirror tower. They used special rigs to simulate the zero-gravity environment, suspending the telescope's components on cables, testing each deployment step in slow motion, checking for any signs of binding or resistance. And every test revealed something new, something that needed fixing, a cable that might snag, a motor that might overheat, a sensor that gave inconsistent readings. Slowly, methodically, they worked through every issue, every risk, every possible failure mode, and by 2019, they were finally ready. Or so they thought. The telescope had passed all its tests. It was fully assembled, fully functional, ready to be shipped to the launch site in French Guiana. But the schedule slipped again. Some components needed additional testing. Some procedures needed to be refined. The launch date moved to 2020, and then COVID hit. The pandemic shut down NASA facilities, delayed shipments, scattered teams across the country working from home. The telescope sat in a clean room in California, waiting. The launch vehicle, an Ariane 5 rocket provided by the European Space Agency, sat in French Guiana, waiting. And the world held its breath, wondering if this telescope, this project that had consumed so much time, so much money, so much hope, would ever actually fly. But eventually, carefully, work resumed. By 2021, the telescope was shipped to the launch site, a journey by boat that took weeks. The telescope sealed in a container, monitored every mile of the way. The container was climate-controlled, maintaining constant temperature and humidity, protecting the telescope from any environmental changes that might damage its delicate instruments or coatings. When the container arrived in French Guiana, it was transported to the launch facility, where teams carefully unpacked the telescope and began the final preparations. They integrated it with the spacecraft bus, the platform that contains the telescope's power systems, communications equipment, and propulsion. They fueled the spacecraft with hydrazine, the propellant it would use for course corrections and for maintaining its orbit at L2. They ran through the launch sequence one last time, checking every connection, every command, every backup system. And on Christmas Day, 2021, 30 years after the project began, James Webb finally left Earth. The launch was perfect. The Ariane 5, Europe's heavy-lift rocket, one of the most reliable launch vehicles ever built, lifted off from the European spaceport in Kourou, French Guiana, at 7:20 a.m. local time. The rocket performed flawlessly, its twin solid rocket boosters providing the initial thrust, its main stage carrying the telescope through the atmosphere, its upper stage delivering Webb to its transfer trajectory toward L2. The precision of the launch was extraordinary. The Ariane 5 placed Webb on a path so accurate that the telescope barely needed to use its own fuel for course corrections, adding years, possibly a decade or more, to its potential lifespan. That extra fuel means Webb can continue operating long past its design life, potentially delivering discoveries for 20 years or more. But the mission was far from over. In fact, the hardest part was just beginning. Over the next month, Webb had to deploy. The sunshield had to unfold. The mirror segments had to extend. The secondary mirror, suspended on a tripod structure, had to lock into place, and every single step had to work. There was no backup plan. If anything failed, the mission was over. The first major milestone came 3 days after launch, when the sunshield pallet was lowered, separating the spacecraft bus from the telescope itself, creating the clearance needed for the sunshield to unfold. Then came the forward and aft momentum flaps, small panels that would help stabilize the sunshield during deployment. Then, the deployable tower assembly extended, pushing the telescope forward, away from the spacecraft bus, creating the gap where the sunshield would eventually sit. And then, the moment everyone had been dreading, the sunshield deployment began. First, the mid-booms extended, pulling the sunshield layers out to their full width. Each layer had to separate from the others, held apart by thin cables and spacers. Then came tensioning, the process of pulling each layer taut, eliminating wrinkles, creating the smooth surfaces needed for thermal insulation. This was done carefully, incrementally, monitoring the tension in each cable, watching for any signs of problems. And when the first layer tensioned successfully, the team celebrated. When the second layer tensioned, they celebrated again. By the time all 5 layers were deployed and tensioned, perfectly flat, perfectly separated, engineers who had worked on the project for decades were crying, hugging each other, overwhelmed with relief and joy, because they knew the mission was going to work. Next came the mirror deployment. The side panels, each containing 3 mirror segments, were folded back during launch to fit inside the rocket fairing. Now they had to swing out, locking into position on either side of the central section. The left panel deployed first, a slow, deliberate process that took several hours. Then the right panel, and when both were locked in place, the full hexagonal shape of Webb's primary mirror was revealed for the first time in space, a golden honeycomb floating against the black, looking like something out of science fiction. But looking right wasn't enough. The mirror had to work right, and that required alignment, one of the most delicate and crucial phases of commissioning. Each of the 18 mirror segments had to be positioned to nanometer precision, adjusted so that they all focused light to the same point, acting as a single, giant mirror rather than 18 separate ones. That took weeks. Engineers used actuators behind each segment, tiny motors that could tilt and shift the mirrors, adjusting them while Webb stared at a single bright star, HD 84406, watching how its light scattered across the segments. At first, it looked like 18 separate stars, 18 blurry dots scattered across the field of view, each one representing the image from a single segment. But slowly, carefully, the engineers nudged the segments together, overlapping the dots, sharpening the focus. They started with coarse adjustments, getting all the segments pointing roughly in the same direction. Then they moved to fine adjustments, aligning the segments to within micrometers. And finally, they did phase alignment, adjusting the position of each segment so that the light waves from all 18 were perfectly in phase, constructively interfering to create the sharpest possible image. When they finally merged into a single, perfect point of light, sharper than anything Hubble could produce, the team knew. It worked. Webb was ready. But there was one more step before science could begin. The instruments needed to be calibrated. Each one had to be tested, characterized, its quirks and behaviors documented. The detectors had to be checked for hot pixels, dead pixels, variations in sensitivity. The optical systems had to be verified, ensuring that the images were sharp across the entire field of view. The spectrographs had to be calibrated, determining the exact relationship between pixel position and wavelength. This process took months, with engineers and scientists working around the clock, analyzing data, refining procedures, writing software to correct for instrumental effects. And by June 2022, 6 months after launch, Webb was finally ready to begin its science mission. And then came the first images. We all saw them. The deep field, SMACS 0723, a patch of sky no bigger than a grain of sand held at arm's length, filled with thousands of galaxies, each one a smudge of light stretched and warped by gravity, some of them shining from over 13 billion years ago. The image was revealed at a White House event, with President Biden presenting it to the world, a moment that captured the public's imagination in a way few scientific achievements do. The image was beautiful, yes, but it was more than that. It was proof that Webb could see what it was built to see, proof that the investment, the delays, the decades of work had been worth it. Because in that single image, we were looking further back in time than we ever had before, seeing galaxies that formed when the universe was still in its infancy, still figuring out how to make stars, still learning the rules. And this was just the beginning. But before we dive deeper into the discoveries, let's take a moment to appreciate what Webb actually is, not just as a telescope, but as an observatory, a platform for doing science. Because Webb isn't like Hubble, where astronauts could visit and upgrade the instruments, install new cameras, fix problems. Webb is at L2, a million miles away, far beyond the reach of any spacecraft we could send to service it. So everything had to work perfectly from the start, and everything had to be designed to last, to keep working for a decade or more without any maintenance. That meant redundancy, backup systems for critical components. It meant careful design of the electronics, radiation hardened to withstand the constant bombardment of cosmic rays and solar particles. It meant thermal management, keeping the cold side cold and the hot side manageable, using passive radiators and careful placement of components. But it also meant flexibility. Webb wasn't designed to do just one thing. It was designed to be a general-purpose observatory, capable of addressing a wide range of scientific questions. That's why it has 4 different instruments, each one optimized for different types of observations. And that's why the telescope's mirror and pointing system are so precise. Webb can point at any target in the sky as long as it's not too close to the Sun, and hold that pointing stable to within milliarc seconds, even while the telescope is orbiting the Sun at L2, even while it's experiencing tiny pushes from solar radiation pressure and the faint drag of interplanetary dust. That stability is crucial for long exposures, for building up signal from faint objects, for doing spectroscopy that requires holding the target precisely aligned with narrow spectrograph slits. And then there's the data. Webb generates enormous amounts of it, gigabytes per day, images and spectra that have to be transmitted back to Earth, processed, calibrated, and delivered to astronomers. The telescope communicates with Earth using the Deep Space Network, a system of large radio antennas located in California, Spain, and Australia, spaced around the globe so that at least one is always in view of Webb. The data is transmitted at about 28 megabits per second when a ground station is in contact, and the telescope stores data on board when no station is available, using a solid-state recorder with 68 gigabytes of capacity. Once the data reaches Earth, it's sent to the Space Telescope Science Institute in Baltimore, where it's processed through automated pipelines that apply calibrations, remove instrumental artifacts, and produce science-ready images and spectra. Those data products are then delivered to the astronomers who requested the observations, usually within a few days of the observation being taken. And after a proprietary period, typically 1 year, the data becomes public, available to anyone who wants to use it. That's an important point. Webb isn't just serving the astronomers who get time on the telescope. It's serving the entire scientific community, and eventually, the public. All of Webb's data, all of its images and spectra, will eventually be freely available in public archives, where anyone with the skills and interest can analyze it, search for new discoveries, test new hypotheses. Some of Webb's most interesting findings have come from astronomers analyzing archival data, looking at images taken for one purpose, but finding something unexpected in the background. Now, let's talk about what makes Webb's infrared vision so powerful. Infrared light, the kind of light Webb detects, has wavelengths longer than visible light, ranging from about 0.6 micrometers, just past the red end of the visible spectrum, to about 28 micrometers, well into what we call the thermal infrared. Why does that matter? Because the universe is full of things that are invisible in visible light, but bright in infrared. Cold things, for instance, things that don't emit enough visible light to see but glow in infrared from their thermal radiation. Brown dwarfs, failed stars that never got hot enough to fuse hydrogen, are almost invisible in visible light but bright in infrared. Protoplanetary disks, the clouds of dust around young stars where planets form, are opaque in visible light but transparent in infrared, allowing Webb to see through the dust and study the forming planets inside. And then there's redshift, one of the most important concepts in cosmology. When the universe expands, it stretches space itself, and anything moving through that space gets stretched along with it, including light waves. Light from distant galaxies, traveling through expanding space for billions of years, gets stretched to longer wavelengths. Ultraviolet light becomes visible light. Visible light becomes infrared, and the farther away the galaxy, the more stretched the light, the more it's shifted toward the red end of the spectrum. That's redshift. We measure it with a number, Z, that represents how much the wavelength has increased. A redshift of Z equals 1 means the wavelength has doubled. A redshift of Z equals 2 means it's tripled. And as redshift gets higher, the light shifts more and more toward the infrared. By the time you're looking at galaxies from the first few 100 million years after the Big Bang, galaxies with redshifts of 10 or 12 or 14, their visible light has been stretched so far that it's now infrared. That's why Hubble, designed primarily for visible and near UV light, could only see the nearest of these early galaxies. And that's why Webb, designed for infrared, can see so many more. But infrared observations come with challenges. The biggest one is heat. Anything warm emits infrared light. You emit it. Your phone emits it. The Earth emits it. And if Webb were warm, it would emit so much infrared light that it would overwhelm any signals from space, like trying to see stars in daylight. That's why Webb has to be cold. And that's why it needs the sun shield. By blocking the sun's heat, the sun shield keeps the telescope at -400 degrees Fahrenheit, cold enough that the thermal emission from the telescope itself is minimal, pushed to much longer wavelengths than the ones Webb is trying to detect. But even that isn't cold enough for MIRI, which looks at longer wavelengths and needs to be even colder. That's why MIRI has its own cryocooler, bringing it down to -447 degrees, just 7 degrees above absolute zero, the coldest temperature possible. Another challenge is the detectors themselves. Infrared light carries less energy than visible light, so it's harder to detect. Infrared detectors have to be incredibly sensitive, able to register single photons, individual particles of light, arriving from distant objects. And they have to be fast, reading out the signal quickly before thermal noise accumulates. The detectors Webb uses are state-of-the-art, developed over decades of research in infrared astronomy. They're made of exotic materials like mercury-cadmium telluride, semiconductors that can detect infrared light but have to be cooled to work properly. At cold temperatures, these materials are sensitive enough to detect a single photon and fast enough to read out thousands of pixels per second, building up images and spectra from the faint signals arriving from the universe. So when Webb looks at the universe, it's not just seeing the same things Hubble saw, but farther or clearer. It's seeing a different universe, one that's invisible to visible light telescopes, a universe of cold objects and distant galaxies and hidden structures. And that's why Webb's discoveries have been so surprising, so challenging to our models, because we built those models based on what we could see with visible light telescopes, and now we're seeing things those telescopes missed, things that change the story. Let's dig deeper into those early galaxies, because they're not just surprising, they're revolutionary. When Webb started finding galaxies at redshifts above 10, existing when the universe was less than 500 million years old, astronomers were excited. These were the galaxies they'd been hoping to find, the first generation, the pioneers of cosmic structure. But when they started analyzing these galaxies in detail, measuring their properties, calculating their masses and ages, things stopped making sense. Take Sears 93316, for example, one of the earliest candidates, possibly existing just 235 million years after the Big Bang. Based on its brightness and color, astronomers estimated its stellar mass, the total mass of stars it contained, at about 100 million times the mass of the Sunday. That might not sound like much compared to the Milky Way's 60 billion solar masses, but remember, this galaxy had only 235 million years to form those stars. To put that in perspective, let's do some math. If the galaxy formed its first stars immediately after the Big Bang, which we know didn't happen, it would need to convert gas into stars at a rate of about half a solar mass per year, continuously, for the entire 235 million years. But galaxies don't form stars continuously. They go through bursts, periods of intense star formation followed by quieter periods. And in the very early universe, conditions were chaotic. Gas was hot and turbulent, and it's not clear that star formation could proceed efficiently. So to build up 100 million solar masses in 235 million years, you probably need star formation rates of several solar masses per year during the active periods, much higher than what the Milky Way does today. But that's not the end of the problem, because stars don't all survive. Massive stars, the ones that form first in young galaxies, live only a few million years before exploding as supernovae. So some of the mass that went into stars has been blown away, recycled back into gas. To end up with 100 million solar masses of stars, you probably had to form significantly more than that initially. And then there's the question of where all that gas came from. In the very early universe, the only elements available were hydrogen, helium, and trace amounts of lithium, produced in the Big Bang. No carbon, no oxygen, no iron, none of the heavy elements that stars need to form planets or that astronomers need to trace stellar populations. So the first stars, the population 3 stars, had to form from pure hydrogen and helium, and those stars were probably massive, much more massive than typical stars today, because without heavy elements to cool the gas, it was harder for small clumps to collapse under their own gravity. Massive stars form quickly and die quickly, enriching the gas with heavy elements. And then the second generation of stars forms, and those can be smaller, more like the Sunday. But all of that takes time, and Sears 93316 didn't have much time. So either our understanding of star formation in the early universe is wrong, or our measurement of this galaxy's mass is wrong, or our interpretation of its redshift is wrong. That last possibility is worth considering. Redshift is measured spectroscopically by looking at the positions of emission or absorption lines in a galaxy's spectrum and comparing them to the wavelengths those lines have in a laboratory. But if a galaxy is very faint, if its spectrum is noisy, there can be ambiguity in identifying the lines. What looks like a hydrogen line at redshift 14 might actually be a different line at redshift 3. That's called the redshift degeneracy problem, and it's been a source of controversy since Webb started finding these high redshift candidates. Some of them have been confirmed with high-quality spectra, and those confirmations are solid. But others remain photometric redshift estimates based on the galaxy's colors in different filters, and those are less certain. One way to resolve the ambiguity is to get better spectra, longer exposures with near-spec that can reveal fainter lines, confirm the redshift unambiguously. And Webb has been doing that, following up on the most interesting candidates, and in most cases, the high redshifts have been confirmed. These galaxies really are as distant as they appear, which brings us back to the question of how they got so massive so quickly. One possibility that's gaining traction is that star formation in the early universe was simply more efficient than we thought, that the conditions back then, high gas densities, frequent collisions between gas clouds, low metallicity, allowed stars to form at rates we've never seen in the modern universe. Another possibility is that these galaxies are experiencing top-heavy initial mass functions, meaning they're forming more massive stars and fewer low-mass stars than galaxies today. Massive stars are more luminous, so a galaxy forming mostly massive stars would appear brighter for a given stellar mass, potentially leading us to overestimate its mass. But there's another twist. Some of these early galaxies aren't just massive. They're compact, with sizes of just a few hundred parsecs, much smaller than typical galaxies today. That high density might be important. If the stars are packed closely together, their combined gravity can help pull in more gas, feeding continued star formation. And the high density might also affect how the galaxy evolves, making it more susceptible to mergers, more likely to form a supermassive black hole at its center, more likely to undergo rapid chemical enrichment. So, these early galaxies might not just be younger versions of galaxies today, they might be fundamentally different objects, governed by different physics, evolving through different pathways. And understanding them requires us to rethink our models, to consider possibilities we hadn't thought of before, and that's where Webb spectroscopy comes in. Because it's not enough to just see these galaxies. We need to understand them, to measure their properties in detail. Webb spectrographs, NIRS-SPEC and NIRIS, can do that. They can capture the light from these faint, distant galaxies and spread it into a spectrum, revealing emission lines from hydrogen, oxygen, carbon, neon, and other elements. Those lines tell us about the galaxy's star formation rate, its chemical composition, its age, the temperature and density of its gas. And by studying many galaxies, building up a statistical sample, astronomers can start to see patterns, to understand what's typical and what's unusual, to test their models against real data. One of the most interesting results from Webb spectroscopy has been the detection of strong emission lines in many early galaxies, lines that indicate vigorous star formation and high ionization. These galaxies aren't just forming stars, they're forming massive stars that emit intense ultraviolet radiation, ionizing the gas around them, creating glowing nebulae. That's important because those massive stars are also the ones that produce heavy elements, enriching the gas with the materials needed for the next generation of stars and planets. So by studying the emission lines, astronomers can trace the chemical evolution of these galaxies, seeing how quickly they're building up metals, how efficiently they're mixing the enriched gas, how the chemical composition varies across the galaxy. And there are puzzles here too. Some early galaxies show surprisingly high levels of oxygen and nitrogen, much higher than expected for their age. Oxygen is produced primarily in massive stars and expelled in supernovae, so it builds up relatively quickly. But nitrogen is thought to come primarily from intermediate mass stars, which live longer, taking hundreds of millions of years to complete their evolution. So finding high nitrogen abundance in galaxies that are only a few 100 million years old is strange. It suggests either that our understanding of nitrogen production is wrong, or that these galaxies are older than they appear, or that there's some other source of nitrogen we haven't considered. These are the kinds of puzzles that keep astronomers up at night. The details that don't quite fit, the clues that something interesting is going on. Let's talk about another mystery Webb has uncovered: the nature of dark matter in these early galaxies. Dark matter, the invisible substance that makes up most of the mass in the universe, is crucial for galaxy formation. It provides the gravitational scaffolding that allows gas to collapse and form stars. But we don't know what dark matter is. We know it's there because we can see its gravitational effects, the way it bends light, the way it affects the motion of galaxies. But we've never detected it directly. And one of the hopes for Webb was that by studying the earliest galaxies, we might learn something about dark matter, about how it clumps, how it interacts with normal matter, whether its properties match our predictions. So far, the results have been mixed. Gravitational lensing studies, which use the distortion of background galaxies by foreground clusters to map the distribution of dark matter, have generally confirmed that dark matter behaves as expected, clumping in halos around galaxies and clusters. But there are hints of small-scale structure, clumps and subhalos that might be smaller than our models predict, or might be more concentrated. These differences are subtle, and more data is needed to confirm them. But if they're real, they could tell us something about the nature of dark matter, about whether it's just one type of particle or a mixture, whether it interacts with itself through forces we don't know about, whether our models of structure formation need to be revised. Now let's talk about the spin asymmetry in more detail, because it's one of the strangest things Webb has found, and it challenges one of the most fundamental assumptions in cosmology. The cosmological principle, the idea that the universe is homogeneous and isotropic, meaning it looks the same in all directions and at all locations on large scales, is the foundation of modern cosmology. It's the assumption that lets us use observations of one part of the universe to make inferences about other parts. It's the reason we can build models of the universe's expansion and evolution that apply everywhere, not just to the specific regions we can observe. But if the spin asymmetry is real, if there really is a preferred direction of rotation for galaxies, then the universe isn't perfectly isotropic. It has structure, orientation, a directionality that our models don't account for. Leo Shamir's study, analyzing 263 spiral galaxies in the Good South field, found that 60% rotated clockwise and 40% counterclockwise, a statistically significant imbalance. But that's just one field, one region of sky. Is the same asymmetry present elsewhere? Shamir and others have looked at data from other surveys using different telescopes, different wavelengths, and they've found similar results. The asymmetry seems to be real, and it seems to get stronger at higher redshifts, suggesting it might be a feature of the early universe that has faded over time as the universe expanded and structures evolved. But why would there be a preferred spin direction? One possibility is that the universe has a net rotation, a spin imparted during the Big Bang or cosmic inflation. That might sound absurd, but it's not ruled out by current observations. We know the universe is expanding, and we have good measurements of the expansion rate, but we don't have good measurements of whether the universe is also rotating. If it is, the rotation would have to be very slow. Otherwise, we would have detected it in the cosmic microwave background, the afterglow of the Big Bang. But a slow rotation below the threshold of current detection could still affect the formation of galaxies, giving them a preferred spin direction aligned with the universe's rotation axis. Another possibility is that the asymmetry is not cosmic but local, related to the motion of our galaxy or the large-scale structure of the nearby universe. The Milky Way is moving through space at about 600 kilometers per second, part of a larger flow of galaxies being pulled toward a massive structure called the Great Attractor. That motion could create a Doppler effect that makes galaxies spinning in one direction appear slightly brighter or bluer, potentially biasing automated classification algorithms that identify spiral arms based on brightness patterns. But if that's the explanation, the asymmetry should disappear when we correct for the Milky Way's motion, and so far, studies that have tried to do that have found the asymmetry persists. A third possibility, and this one is more exotic, relates to the idea that our universe might have been born from a rotating black hole in a parent universe. This is a speculative idea, proposed by physicist Nikodem Poplavsky, based on a variant of general relativity that includes torsion, a twisting of spacetime that's usually neglected. In this model, when a massive star collapses to form a black hole, the matter doesn't actually collapse to a singularity. Instead, it bounces, expanding into a new universe on the other side of the event horizon, a baby universe that inherits some of the properties of the parent, including its rotation. If our universe formed this way, it might have a primordial spin, a rotation imparted by the black hole it emerged from, and that spin might affect the formation of galaxies, giving them a preferred orientation. Most cosmologists don't take this idea seriously because it's based on a non-standard version of general relativity and doesn't have strong observational support. But it's worth mentioning because it shows the range of possibilities, the kinds of explanations scientists are willing to consider when faced with data that doesn't fit the standard models. The truth is, we don't know yet whether the spin asymmetry is real or an artifact, whether it's cosmic or local, whether it requires new physics or just better data. And that's okay. That's how science works. You find something strange, you investigate it, you gather more data, you test hypotheses, and eventually you figure it out. Webb is still early in its mission, and the samples are still small. As more galaxies are observed, as larger and more diverse datasets are collected, we'll be able to test these ideas more rigorously, see whether the asymmetry holds up, whether it varies with redshift or position on the sky, whether it's correlated with other properties of galaxies. And whatever we find, it will teach us something about the universe, about its structure, its evolution, its fundamental nature. Now let's turn our attention to supermassive black holes, because Webb's findings in this area have been just as revolutionary as its discoveries about early galaxies. Black holes are among the most extreme objects in the universe, regions of space-time where gravity is so strong that nothing, not even light, can escape. We've known about black holes for decades, predicted by Einstein's general relativity, detected through their effects on nearby matter, but we've never fully understood them, especially the supermassive ones, the monsters that lurk at the centers of galaxies, with masses of millions or billions of times the sunday. Where do they come from? How do they grow so large? And how do they influence the galaxies they inhabit? The traditional story, as I mentioned earlier, is that supermassive black holes grow from stellar mass seeds, black holes formed from the collapse of massive stars that then accrete matter over billions of years, slowly growing. But that story has problems that Webb has made impossible to ignore. Because Webb has found supermassive black holes in galaxies that existed just 500 or 600 million years after the Big Bang, black holes with masses of millions or even hundreds of millions of solar masses. And that's not enough time for them to have grown from stellar seeds, not at the rates we think are possible. The Eddington limit, the maximum rate at which a black hole can accrete matter, is determined by the balance between gravity pulling matter in and radiation pressure pushing it out. When matter falls toward a black hole, it heats up, emitting radiation. If the radiation is too intense, it pushes the infalling matter away, shutting down accretion. For a solar mass black hole, The Eddington limit corresponds to accreting about 1/10,000,000th of a solar mass per year. For a million solar mass black hole, it's about 1/100th of a solar mass per year. Now, if a stellar mass black hole, say 50 solar masses, accretes continuously at the Eddington limit, doubling its mass every few tens of millions of years, it can grow to 1,000,000 solar masses in about 400 million years. That's barely enough time if the black hole started forming immediately after the Big Bang, which we know didn't happen. Stars had to form first, live, die, create the first black holes. So, realistically, stellar mass black holes probably didn't start forming until at least 100 million years after the Big Bang, leaving only a few hundred million years to grow to 1,000,000 solar masses. And Webb has found black holes that are even more massive, requiring even more growth in even less time. So either these black holes are accreting faster than the Eddington limit, which is possible under special conditions, or they didn't start as stellar mass black holes, they started bigger. And that's where direct collapse black holes come in. The idea of direct collapse black holes has been around for a while, but it's always been controversial because the conditions required are very specific and might not have been common in the early universe. For a direct collapse to work, you need a massive cloud of gas, at least 100,000 solar masses, preferably more. And you need that gas to be hot, around 10,000 degrees Kelvin, hot enough that it doesn't fragment into smaller clumps that would form stars instead. And you need it to be metal-free, or at least metal-poor, because heavy elements help cool the gas, making it fragment. If you can get all those conditions at once, the gas cloud can collapse directly under its own gravity, bypassing the star formation phase, creating a black hole of thousands or tens of thousands of solar masses in one go. That gives you a massive seed. And from there, it's much easier to grow to 1,000,000 or billion solar masses in the time available. But how do you get those conditions? One possibility is in the halos of dark matter, the invisible structures where galaxies form. In the early universe, dark matter clumped under its own gravity, forming halos that attracted normal matter, gas that fell in and began to form stars. But not all halos formed stars immediately. Some halos, particularly those that were bathed in intense ultraviolet radiation from nearby star-forming regions, might have had their gas heated to high temperatures, preventing cooling and fragmentation. In those halos, the gas could accumulate without forming stars, building up to the critical mass needed for direct collapse. And when it finally collapsed, it would form not a star, but a black hole. This scenario, called atomic cooling, halos with H2 suppression, has been studied extensively in simulations, and it seems to work. But we've never observed it directly, never caught a direct collapse black hole in the act of forming, until, possibly, the Infinity Galaxy. The Infinity Galaxy, discovered by Webb in July 2025, is a pair of colliding galaxies whose combined shape resembles an infinity symbol. It's a beautiful image, but the real interest is at the center, where the two galactic nuclei are colliding, creating an environment of extreme density and turbulence. There, Webb detected a supermassive black hole actively feeding, pulling in gas, emitting enormous amounts of energy. Based on the black hole's brightness and the properties of the surrounding gas, researchers calculated that this might be a direct collapse event, a massive gas cloud collapsing directly into a black hole as we watch. It's not definitive. The black hole might have formed earlier, through conventional means, and is just experiencing an unusually intense feeding episode triggered by the collision. But the possibility is tantalizing. If this really is a direct collapse, if we're seeing the formation of a supermassive black hole in real time, it would be a major confirmation of the theory, a direct observation of a process we've only been able to simulate until now. But even if the Infinity Galaxy isn't a direct collapse, Webb's other black hole findings are significant. The telescope has identified dozens of active galactic nuclei in the early universe, quasars powered by supermassive black holes feeding on gas and dust. These quasars are incredibly bright, some of them outshining their entire host galaxies, visible across billions of light years. And by studying them, measuring their spectra, analyzing the properties of the gas around them, astronomers can learn about the black holes themselves, their masses, their spins, how fast they're growing. Webb's infrared sensitivity is particularly valuable here because many early quasars are obscured by dust, invisible light, but bright in infrared. By observing in infrared, Webb can penetrate the dust, revealing quasars that would otherwise be hidden, building a more complete census of supermassive black holes in the early universe. And that census is revealing patterns. It seems that supermassive black holes were more common in the early universe than we expected, present in a larger fraction of galaxies, growing more quickly. And they seem to be correlated with their host galaxies, with more massive galaxies hosting more massive black holes, even at early times. That correlation suggests that black holes and galaxies co-evolve, that they influence each other's growth. The black hole's gravity attracts gas, pulling it in, but as the gas falls toward the black hole, it heats up and emits radiation, powerful winds and jets that can blow gas out of the galaxy, quenching star formation. This feedback mechanism is thought to be crucial for regulating galaxy growth, preventing galaxies from forming too many stars, keeping them from becoming too massive. And Webb is providing the data needed to test these ideas, to see how feedback operates in the early universe, how strong it is, how it varies with galaxy mass and environment. One of the most intriguing findings is that some early galaxies already show signs of feedback, regions where star formation has been suppressed, cavities blown out by black hole winds. These are the quiescent galaxies I mentioned earlier, galaxies that have stopped forming stars despite being young. And it seems that black hole feedback might be responsible, that the supermassive black hole at the center of the galaxy grew rapidly, fed voraciously, and then expelled the remaining gas, shutting down star formation. If that's true, it means that black holes play a crucial role in shaping galaxies, not just in the modern universe, but even in the first billion years. And it means that understanding galaxy evolution requires understanding black holes, how they form, how they grow, how they interact with their surroundings. Now let's talk about gravitational lensing in more detail, because it's not just a pretty effect. It's one of the most powerful tools in astronomy, allowing us to study objects that would otherwise be too faint or too distant to detect. Gravitational lensing occurs when light from a distant object passes near a massive foreground object, like a galaxy or galaxy cluster. The foreground object's gravity bends the light's path, focusing it, amplifying it, sometimes creating multiple images of the same background object. Einstein predicted this effect in 1915 based on his general theory of relativity, and it was first observed in 1919 during a solar eclipse, when stars near the sun appeared, shifted from their usual positions, their light bent by the sun's gravity. That observation made Einstein famous, confirming his theory and showing that gravity really does curve space-time. But gravitational lensing is more than just a confirmation of general relativity. It's a tool for studying both the lensing object and the lensed object. By analyzing the distortion of the lensed light, measuring the positions and shapes of the multiple images, astronomers can reconstruct the mass distribution of the lensing object, mapping where the mass is, how it's distributed, how much is ordinary matter and how much is dark matter. And by studying the magnification, they can learn about the lensed object, using the lens as a natural telescope that makes faint objects visible. Webb has been using gravitational lensing extensively, studying both the lenses and the lensed objects, learning about galaxy clusters, dark matter, and the most distant galaxies in the universe. One of Webb's most spectacular lensing observations targeted the galaxy cluster SMACS 0723, the same cluster featured in that first deep field image. The cluster, located about 4.6 billion light-years away, is massive enough to significantly bend the light from galaxies behind it, creating arcs and multiple images scattered across the field. Webb's infrared sensitivity allowed it to detect lensed galaxies at redshifts of 10, 11, even higher, galaxies that existed just a few 100 million years after the Big Bang. And the magnification from the lens made these galaxies bright enough to study in detail, to measure their spectra, to analyze their chemical composition, to understand their star formation histories. Without the lens, many of these galaxies would be too faint to detect, even with Webb. but with the lens providing a magnification of 10x, 20x, sometimes even 100x, they become accessible. Webb has also studied caustic crossing events, rare occurrences where a lensed object crosses a caustic, a region of extremely high magnification in the lensing geometry. When that happens, the object can brighten dramatically, sometimes by factors of hundreds or thousands, for a brief period. Caustic crossings are unpredictable, but when they occur, they provide a unique opportunity to study the lensed object at incredibly high resolution, seeing details that would normally require a telescope much larger than Webb. Astronomers have used caustic crossings to study individual star-forming regions in distant galaxies, measuring their sizes, their luminosities, their stellar populations, learning about how star formation proceeds in environments very different from the local universe. And then there are lensed supernovae, like Snoppy, the triply lensed supernova I mentioned earlier. When a supernova occurs in a lensed galaxy, its light follows multiple paths through the lensing cluster, arriving at Earth at different times. The time delays depend on the path's lengths and the gravitational potential they traverse. By measuring those delays, astronomers can determine the mass distribution in the lensing cluster and the expansion rate of the universe, the Hubble constant. This method, called time delay cosmology, is independent of the other methods used to measure the Hubble constant, and it provides a crucial cross-check. The Hubble tension, the discrepancy between measurements from the cosmic microwave background and local distance ladder, is one of the most significant problems in cosmology right now. If the discrepancy is real, it might indicate new physics, something we don't understand about dark energy or the expansion history of the universe. But if it's an artifact of systematic errors in one or both methods, that's important to know too. Lensed supernovae offer a way to settle the question, and Webb is perfectly suited to finding and studying them. Webb has also observed strong lensing of quasars, where multiple images of the same quasar appear around a lensing galaxy. These systems are valuable for studying both the quasar and the lens. The quasar's light, split into multiple images, can be analyzed for time variability, flickering on timescales of days or weeks as the black hole's accretion disk fluctuates. By comparing the variability in different images, which arrive at different times due to the different light paths, astronomers can measure the time delays and learn about the lensing galaxy's mass. And they can study the quasar itself, measuring its spectrum, analyzing the properties of the accreting gas, learning about the black hole's mass and spin. One particularly interesting application is using lensed quasars to study the intergalactic medium, the diffuse gas that fills the space between galaxies. As the quasar's light travels through the intergalactic medium, it encounters clouds of hydrogen and helium, which absorb light at specific wavelengths. Those absorption lines, called the Lyman alpha forest, provide a detailed map of the gas along the line of sight, showing its density, temperature, and motion. By studying the Lyman alpha forest in lensed quasars, astronomers can learn about the structure of the intergalactic medium in the early universe, how it evolved, how it was enriched with heavy elements from supernovae, how it was ionized by the first stars and quasars. Now let's turn our attention back to exoplanets, because this is where Webb is making some of its most exciting contributions, bringing us closer to answering the question, are we alone? The detection of dimethyl sulfide, or DMS, on K218b was a watershed moment, the first time we've detected a molecule on an exoplanet that, on Earth, is only produced by life. But let's be clear about what that means and what it doesn't mean. On Earth, DMS is produced primarily by marine phytoplankton, microscopic algae that live in the ocean. These organisms produce DMS as a byproduct of their metabolism, and the molecule plays a role in cloud formation, affecting Earth's climate. But just because DMS is biogenic on Earth doesn't mean it's biogenic everywhere. Alien biochemistry might work differently. There might be abiotic processes, chemical reactions that don't involve life, that can produce DMS under the right conditions. We don't know of any such processes on Earth, but that doesn't mean they don't exist elsewhere. So the detection of DMS on K218b is provocative, intriguing, worth following up on, but it's not proof of life. To be sure, we'd need more data, more observations, looking for other molecules that might confirm or rule out biological processes. We'd want to see a pattern of molecules that make sense together, a combination that's hard to explain without life. Methane and oxygen together, for instance, would be a strong biosignature because methane and oxygen react with each other, destroying each other, so finding them both in an atmosphere suggests something is continuously producing them, replenishing the supply. On Earth, that something is life. Photosynthetic organisms producing oxygen and methanogenic bacteria producing methane. Finding both on an exoplanet would be compelling evidence for life, though still not definitive. K218b is interesting not just because of DMS, but because of its overall properties. It's a Haitian world, a type of planet that's neither rocky like Earth nor gaseous like Neptune, but somewhere in between. Haitian worlds, named for their hydrogen-rich atmospheres and potential for global oceans, were proposed as a new class of potentially habitable planets just a few years ago. They're more common than Earth-like planets because they can be more massive, and more massive planets are easier to detect. And they might be habitable despite being very different from Earth because they could have liquid water oceans beneath thick atmospheres, kept warm by greenhouse heating or tidal heating. K218b fits that profile. It's about 2.6 times Earth's radius and about 9 times Earth's mass, with a thick hydrogen-helium atmosphere and possibly a water ocean beneath. The temperature is estimated to be in the range where liquid water could exist, though the exact conditions depend on the atmosphere's composition and thickness. Webb's observations of K218b have revealed water vapor, methane, and carbon dioxide, all molecules you'd expect on a water-rich world with a thick atmosphere. The combination of methane and CO2 is particularly interesting because on Earth, the ratio of these gases is controlled by biological processes. But on K218b, it's not clear what's controlling them. It could be geology, chemical reactions in the atmosphere, or ocean, or it could be biology. To distinguish between these possibilities, we need more observations, higher signal-to-noise spectra, detections of additional molecules. Webb is continuing to observe K218b, building up more data, and other telescopes, both ground-based and space-based, are contributing as well. Over the next few years, we should have a much clearer picture of what's happening on this planet, whether it really does have DMS, whether there are other biosignatures, whether it's plausibly habitable. But K218b is just one planet. Webb is studying dozens of exoplanets, building a comprehensive picture of atmospheric diversity, learning what kinds of molecules are common, what kinds are rare, what combinations are possible. Hot Jupiters like WASP-39b, WASP-17b, WASP-18b have been observed in detail, revealing clouds made of silicates, metal oxides, even sodium and potassium. These planets are scorched by their proximity to their stars, with temperatures reaching thousands of degrees, hot enough to vaporize rock and metal. The atmospheres are exotic, unlike anything in our solar system, with weather systems driven by intense heating on the day side and cooling on the night side, creating supersonic winds that transport heat around the planet. Webb has also studied cooler planets, mini-Neptunes and sub-Neptunes, worlds with masses between Earth and Neptune that have thick hydrogen-helium atmospheres but might have rocky or icy cores beneath. These planets are the most common type in the galaxy, more numerous than Earth-like planets or gas giants. Yet we don't have any in our solar system, so we don't really understand them. Webb's observations are filling that gap, revealing the diversity of mini-Neptunes, their atmospheric compositions, their cloud properties, their thermal structures. Some have clear atmospheres, allowing starlight to penetrate deep, revealing molecular absorption features. Others have thick clouds or hazes that obscure the deeper layers, making it harder to study the atmosphere's composition. And then there are the rocky planets, the ones that might be most like Earth, the ones where we might find signs of life. Webb has started studying these too, though they're challenging targets because they're small, dim, and their atmospheres, if they have them, are thin and difficult to detect. GJ 486b, a rocky planet about 26 light-years away, has been observed by Webb, looking for signs of an atmosphere. the results have been ambiguous. Some observations suggest a thin atmosphere, possibly with water vapor or carbon dioxide. Others suggest no atmosphere at all, just bare rock. The planet orbits close to its star, a red dwarf, and red dwarfs are active, emitting intense flares and radiation that can strip away a planet's atmosphere over time. So even if GJ 486b had an atmosphere initially, it might have lost it, eroded away by its star's energy. That's one of the challenges of studying planets around red dwarfs. Red dwarfs are the most common type of star, making up about 70% of all stars in the galaxy, and they're long-lived, burning for trillions of years, much longer than stars like the Sunday. So if life exists in the universe, there's a good chance some of it is on planets orbiting red dwarfs. But red dwarfs are also active, especially when they're young, bombarding their planets with flares, ultraviolet radiation, and stellar winds. And because red dwarfs are dim, their habitable zones, the regions where liquid water can exist, are close to the star, making planets even more vulnerable to this activity. So whether planets around red dwarfs can actually be habitable is an open question, one that Webb is helping to answer by studying the atmospheres of these planets, seeing whether they've been stripped away or whether some planets have managed to hold on to their atmospheres, perhaps protected by strong magnetic fields or replenished by volcanic outgassing. Webb is also contributing to the study of directly imaged exoplanets, planets that are visible as separate points of light from their stars. These are rare because planets are much fainter than stars, typically 1,000,000 or billion times fainter, and they're close to their stars, making them hard to separate. But some planets, particularly young gas giants that are still hot from their formation, emit enough infrared light to be detected directly. And by imaging them, measuring their light, we can study their atmospheres in detail without having to wait for transits or rely on the starlight filtering through the atmosphere. Webb captured its first direct image of an exoplanet in September 2022, HIP 65426b, a gas giant about 350 light-years away. The image showed the planet as a distinct point of light, separated from its star by about 100 astronomical units, roughly the distance from the Sun to Pluto. And Webb's infrared sensitivity allowed it to capture not just an image, but a spectrum, revealing the planet's atmospheric composition, its temperature profile, its cloud structure. The spectrum showed methane, water vapor, and hints of other molecules, consistent with a young gas giant still cooling from its formation. And by comparing the spectrum to models, astronomers could estimate the planet's mass, about 6 to 8 times Jupiter's mass, and its age, about 15 to 20 million years, incredibly young compared to Jupiter's 4.6 billion years. Observations like this are crucial for understanding how planets form and evolve, because young planets, still glowing with the heat of their formation, reveal details that older, cooler planets hide. Over the next few years, Webb will image dozens more exoplanets, building a catalogue of directly imaged worlds, learning about their atmospheres, their masses, their orbits, their formation histories. And as Webb continues its exoplanet work, the next generation of telescopes is already being planned. The Habitable Worlds Observatory, NASA's proposed successor to Webb, will be designed specifically to find and study Earth-like planets around nearby stars. It will use a coronagraph or star shade to block the light from the star, allowing it to image planets that are much fainter and much closer to their stars than current telescopes can see. And by studying these planets, measuring their spectra, analyzing their atmospheres, we'll be able to determine whether they're truly Earth-like, whether they have water, oxygen, ozone, methane, the kinds of molecules that might indicate life. The Habitable Worlds Observatory is still in the planning stages, decades away from launch, but Webb is paving the way, proving the techniques, building the knowledge base, showing what's possible. And every exoplanet Webb studies, every molecule it detects, brings us closer to answering the biggest question of all: are we alone in the universe? Let's return to our own solar system, because Webb's observations here have been just as valuable as its studies of distant galaxies and exoplanets. Take Mars, for example. We've been studying Mars for decades, with orbiters, landers, and rovers, mapping its surface, analyzing its rocks, searching for signs of ancient life. But Webb brings a new perspective, a global view in the infrared that reveals features invisible to other telescopes. Webb has captured high-resolution images of Mars, showing dust storms as they develop, tracking their movement across the planet, measuring their thickness and composition. It's observed the polar ice caps, mapping their seasonal changes, measuring the amounts of water ice and carbon dioxide ice as they sublimate and refreeze. And it's studied the atmosphere, measuring the abundance of water vapor, carbon dioxide, and trace gases, learning about the planet's climate and how it varies with location and season. One of Webb's most interesting Mars observations focused on the planet's ancient riverbeds and lakebeds, features carved by liquid water billions of years ago when Mars was warmer and wetter. By studying these features in the infrared, Webb can detect minerals that formed in the presence of water, clays, and carbonates that tell us about Mars's past climate, about whether the water was acidic or alkaline, whether it lasted for millions of years or was ephemeral, appearing briefly during volcanic eruptions or asteroid impacts. These observations complement the work being done by rovers on Mars's surface, providing context, showing how the local features studied by rovers fit into the planet's global history. Webb has also observed Jupiter in unprecedented detail, studying the Great Red Spot, the giant storm that's been raging for at least 350 years. Webb's infrared observations reveal the storm's structure, showing how temperature varies with depth, how winds circulate, how the storm interacts with the surrounding atmosphere. The Great Red Spot has been shrinking for decades, and scientists don't fully understand why. Webb's observations are helping to answer that question, showing how the storm exchanges energy with its environment, how it's affected by Jupiter's deep atmospheric circulation, whether it might eventually disappear or stabilize at a smaller size. Webb has also studied Jupiter's auroras, the glowing curtains of light near the poles created when charged particles from the Sun are funneled by Jupiter's magnetic field and slam into the atmosphere. Webb's infrared view reveals the auroras in detail, showing their structure, their dynamics, how they respond to changes in the solar wind and in Jupiter's magnetosphere. And then there are Jupiter's moons, particularly Europa and Ganymede, two of the most intriguing targets in the search for life in our solar system. Europa, as I mentioned, has a subsurface ocean beneath its icy crust, kept liquid by tidal heating from Jupiter's gravity. Webb has confirmed the presence of water vapor plumes venting from Europa's surface, and it's analyzed the composition of those plumes, looking for salts, organic molecules, anything that might tell us about the ocean below. The results have been promising. Webb has detected sodium chloride, common table salt, in the plumes, suggesting that the ocean is salty, similar in some ways to Earth's oceans. And it's detected organic molecules, simple carbon compounds that could be the building blocks of more complex chemistry. These findings don't prove that life exists in Europa's ocean, but they show that the ocean has the right chemistry, the right ingredients, to potentially support life. Ganymede, Jupiter's largest moon, is another ocean world, with a subsurface ocean buried beneath a thicker ice crust than Europa's. Ganymede is unique because it's the only moon in the solar system with its own magnetic field, generated by a liquid iron core. Webb has studied Ganymede's surface, mapping its composition, identifying regions enriched in water ice, frozen carbon dioxide, and salts. And it's measured the moon's tenuous atmosphere, a thin envelope of oxygen produced when charged particles from Jupiter's magnetosphere strike the surface and break apart water molecules, releasing oxygen into space. By studying Ganymede's atmosphere and surface, Webb is helping scientists understand the moon's geology, its interior structure, its potential for habitability. Webb has also turned its attention to Saturn and its moons, particularly Titan and Enceladus. Titan, Saturn's largest moon, is the only moon in the solar system with a thick atmosphere, denser than Earth's, made mostly of nitrogen with traces of methane and other hydrocarbons. The atmosphere is so thick and hazy that the surface is invisible in visible light. But Webb's infrared eyes can penetrate the haze, revealing features on the surface: lakes and seas of liquid methane and ethane, hydrocarbon glaciers, dunes made of organic particles. Titan is a strange world, with a methane cycle analogous to Earth's water cycle, with liquid methane rain, rivers, and lakes, with clouds of methane and ethane drifting through the atmosphere. Webb's observations are revealing the details of this cycle, showing how methane is distributed, how it moves through the atmosphere, how it interacts with the surface. Enceladus, a small moon orbiting inside Saturn's rings, is another ocean world, with geysers erupting from its south pole, spewing water vapor, ice particles, and organic molecules into space. These geysers are powered by tidal heating, similar to Europa, and they provide a window into Enceladus's subsurface ocean, allowing scientists to study the ocean's composition without having to drill through the ice. Webb has observed Enceladus's geysers, measuring their composition, detecting water, carbon dioxide, methane, and simple organic molecules like formaldehyde and acetylene, and it's detected salts and silicates, particles that suggest the ocean is in contact with a rocky seafloor, where hydrothermal vents might be providing energy and nutrients, creating environments where life could potentially exist. And Webb hasn't stopped there. It's observed Uranus and Neptune, the ice giants, studying their atmospheres, their rings, their moons. Uranus is a particularly interesting target because of its extreme axial tilt, which gives it seasons unlike any other planet. Webb's observations have revealed details of Uranus's atmosphere, showing cloud patterns, storms, and thermal features that vary with season and latitude. Neptune, the outermost planet, is also fascinating, with winds that are the fastest in the solar system, reaching speeds of over 2,000 kilometers per hour. Webb's infrared observations have revealed Neptune's ring system in detail, showing the thin arcs that appear and disappear, the clumps and gaps that suggest interactions with nearby moons, the dust that scatters sunlight and creates the faint glow visible from Earth. Webb has also studied comets, those icy wanderers from the outer solar system that periodically swing through the inner solar system, heating up, releasing gas and dust, creating the beautiful tails we see from Earth. Comet 238P, Reid, which I mentioned earlier, is particularly interesting because it's a main belt comet, an object that orbits in the asteroid belt between Mars and Jupiter but behaves like a comet, developing a tail when it approaches perihelion, the point in its orbit closest to the Sunday Webb, detected water vapor from 238P, confirming that it contains ice, but surprisingly, no carbon dioxide. Most comets have both water and CO2 ice, so the absence of CO2 on 238P is puzzling. It might mean the comet formed in a warmer region of the solar system, where CO2 ice couldn't condense. Or it might mean the CO2 has been lost over billions of years, sublimated away during previous perihelion passages. Either way, it tells us something about the comet's history, about where it formed, how it evolved, how it ended up in the asteroid belt. Webb has also observed near-Earth asteroids, objects that pass close to Earth and could potentially pose an impact hazard. Asteroid 2024 YR4, which I mentioned earlier, is one example. By measuring the asteroid's size, shape, rotation, and surface composition, Webb is helping scientists assess the risk these objects pose and plan potential deflection missions if necessary. NASA's DART mission, which successfully deflected the asteroid Dimorphos in 2022, demonstrated that we can change an asteroid's orbit given enough warning. But to use that capability effectively, we need to know which asteroids are potentially hazardous, where they are, where they're going, what they're made of. Webb is contributing to that effort, providing detailed observations of near-Earth asteroids, building the database we need to protect our planet. Now let's talk about star formation and stellar evolution in more depth, because these processes are fundamental to understanding the universe. Stars are the engines of cosmic evolution, converting hydrogen into helium and heavier elements, releasing energy that lights up galaxies, creating the conditions for planets and life to form. But star formation is a complex process, one that we still don't fully understand despite decades of study. It begins with a giant molecular cloud, a cold, dense region of gas and dust, often hundreds of light years across, containing enough material to form thousands or millions of stars. These clouds are found throughout the galaxy, in spiral arms, near the galactic center, anywhere gas has accumulated and cooled. They're mostly hydrogen, about 70%, with helium making up most of the rest, and traces of heavier elements like carbon, oxygen, and nitrogen locked up in molecules like carbon monoxide, water, and ammonia. The clouds are cold, just a few tens of degrees above absolute zero, and their internal pressure is low, making them prone to collapse under their own gravity. But collapse doesn't happen everywhere at once. It starts in small regions, overdense clumps where gravity is stronger, pulling in more material, creating a feedback loop that accelerates the collapse. As the clump collapses, it heats up because gravitational potential energy is converted to kinetic energy and then to thermal energy as particles collide. But the clump also radiates away some of that heat, cooling through infrared emission from dust grains and molecular transitions. As long as the clump can cool efficiently, it continues to collapse, becoming denser and hotter. Eventually, the core becomes so dense and hot that it's opaque to radiation, unable to cool efficiently. At that point, the collapse slows, and the core becomes a protostar, a hot, dense object that's not yet fusing hydrogen but is glowing from the heat of its contraction. The protostar continues to grow, pulling in material from the surrounding cloud, building up its mass. As it does, it spins faster because of conservation of angular momentum, and it flattens into a disk, the protoplanetary disk where planets will eventually form. Material from the disk spirals inward, falling onto the protostar, releasing energy, heating the disk. And some of that material doesn't make it to the star. Instead, it's ejected in jets, narrow streams of gas that shoot out along the star's rotation axis at speeds of hundreds of kilometers per second. These jets are driven by magnetic fields, twisted and amplified by the rotating disk that channel the gas outward, clearing away the surrounding material, creating cavities in the cloud. Webb has imaged these jets in stunning detail, revealing their structure, their variability, their interactions with the surrounding gas. One of Webb's most beautiful images is of HH-211, a protostar and its bipolar jets, captured with NIRCam in near-infrared light. The image shows the jets as bright, narrow streams extending outward from the protostar, with knots and bow shocks where the jets slam into the surrounding gas, heating it, creating shock waves. The protostar itself is buried in a thick cocoon of dust, invisible in visible light, but bright in infrared. Webb's image reveals the structure of that cocoon, the dense core where the star is forming, the surrounding envelope of gas still falling inward, the disk where planets might one day form. And by analyzing the spectrum, scientists can measure the temperature, density, and composition of the gas, learning about the conditions under which stars form, how long the process takes, what determines whether a star becomes massive or low mass. As the protostar continues to grow, it eventually reaches a critical point. If it accretes enough mass, about 0.08 solar masses, the core becomes hot enough and dense enough to ignite hydrogen fusion, the nuclear reaction that powers stars, converting hydrogen into helium and releasing energy in the form of photons and neutrinos. At that point, the protostar becomes a main sequence star, stable, shining steadily for millions or billions of years, depending on its mass. Massive stars, more than about 10 solar masses, burn through their fuel quickly, fusing hydrogen, then helium, then carbon, oxygen, neon, all the way up to iron in just a few million years. Low-mass stars, less than about half the Sun's mass, burn slowly, taking tens or even hundreds of billions of years to exhaust their hydrogen, outliving the current age of the universe. Webb has studied stars at all stages of their lives, from protostars still, gathering mass to main sequence stars in the prime of their lives, to evolved stars nearing the end. One of its targets has been Betelgeuse, a red supergiant star in the constellation Orion, one of the brightest stars in the sky. Betelgeuse is massive, about 20 times the Sun's mass, and it's nearing the end of its life. It's already exhausted its core hydrogen, fused it into helium, and moved on to helium fusion, creating carbon and oxygen. Eventually, it will fuse those elements into heavier ones, building up an iron core, and when the iron core reaches a critical mass, about 1.4 solar masses, it will collapse, triggering a supernova explosion that will briefly outshine the entire galaxy. We don't know exactly when that will happen. It could be tomorrow, or it could be 100,000 years from now. But when it does, it will be spectacular, visible in daylight from Earth, creating a new star in the sky for weeks or months before fading. Webb observed Betelgeuse after the Great Dimming, an event in late 2019 and early 2020 when the star suddenly faded to about 40% of its usual brightness, sparking speculation that it might be about to go supernova. But Webb's observations, along with data from other telescopes, showed that the dimming was caused by a dust cloud ejected from the star's surface that temporarily blocked our view. Betelgeuse is a variable star, pulsating with a period of about 400 days, expanding and contracting, shedding mass in a stellar wind that carries away gas and dust. Sometimes, that dust condenses into clouds that obscure the star, making it appear dimmer. Webb's infrared observations penetrated the dust, revealing the star itself, measuring its temperature, its size, its chemical composition, confirming that the dimming was temporary and that Betelgeuse, while certainly old and nearing the end of its life, wasn't about to explode just yet. Webb has also studied planetary nebulae, the glowing shells of gas ejected by dying stars, and supernova remnants, the expanding debris from stars that have already exploded. One of its most striking images is of the Southern Ring Nebula, which I mentioned earlier, showing the intricate structure of the ejected gas, the binary star system at its center, the chemical composition of different regions. By studying planetary nebulae and supernova remnants, astronomers can learn about stellar evolution, about how stars live and die, about how the elements they produce are spread throughout the galaxy. Every atom in your body, except for hydrogen, was created in a star, either through fusion in the core or in the explosion that ended the star's life. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was forged in stars and dispersed into space, eventually finding its way into the gas cloud that collapsed to form our solar system. We are, quite literally, made of stardust, and Webb is helping us understand that process, tracing the life cycle of matter from stars to gas clouds to planets to life. Let's talk about the broader implications of Webb's findings, because they go beyond individual discoveries. They're challenging our understanding of the universe at a fundamental level, forcing us to reconsider models that have worked well for decades, opening up new questions that we didn't even know to ask. Take the standard model of cosmology, the lambda CDM model, which describes the universe as consisting of ordinary matter, about 5%, dark matter, about 27%, and dark energy, about 68%. With the universe expanding at an accelerating rate driven by dark energy, this model has been incredibly successful, explaining the cosmic microwave background, the large-scale structure of the universe, the distribution of galaxies, the abundance of light elements. But Webb's observations of early galaxies, massive and mature galaxies appearing earlier than the model predicts, are raising questions. Are we missing something in our understanding of galaxy formation? Are the initial conditions different than we thought? Is dark matter more complicated than a simple cold, non-interacting particle? Some researchers have suggested that the lambda CDM model might need modifications, tweaks to the parameters, additions of new physics. Others have proposed more radical alternatives, like modified gravity theories that change the way gravity works on large scales, eliminating the need for dark matter. But most cosmologists are cautious, waiting for more data, more observations, before abandoning a model that's worked so well for so long. And that's the right approach. Science progresses by testing models against observations, looking for discrepancies, and then figuring out what needs to change. Sometimes it's the model, sometimes it's the observations, which might have systematic errors or biases. And sometimes it's our interpretation of the observations, the assumptions we make about what we're seeing. Webb is providing the data needed to test these ideas, to distinguish between competing explanations, to see what fits and what doesn't. And as the data accumulates, as patterns emerge, we'll get a clearer picture of what's going on, whether the lambda CDM model needs tweaking or overhauling, whether our understanding of the early universe is fundamentally flawed or just incomplete. And whatever we find, it will be progress. Because science isn't about being right, it's about getting less wrong, about refining our models, about building a picture of the universe that matches reality more and more closely. And Webb is accelerating that process, providing observations that are pushing the boundaries of our knowledge, forcing us to think harder, to question our assumptions, to explore possibilities we hadn't considered. Now let's talk about the future, because Webb's mission is far from over. The telescope was designed to operate for at least 10 years, and with the fuel it has left, thanks to the precise launch, it could last 20 years or more. That means decades of observations, thousands of images and spectra, discoveries we can't even imagine yet. And as Webb continues its work, other telescopes are being planned and built. Telescopes that will complement Webb's observations, fill in the gaps, push even further into the unknown. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2022, will have a field of view 100 times larger than Hubble's, allowing it to survey vast areas of sky, finding millions of galaxies, mapping the large-scale structure of the universe, studying dark energy by observing how the expansion of the universe has changed over time. The extremely large telescope, a ground-based observatory being built in Chile, will have a primary mirror 39 meters in diameter, the largest optical telescope ever built. It will have unprecedented resolution, able to directly image exoplanets, study their atmospheres, even resolve individual stars in nearby galaxies. The Square Kilometre Array, a radio telescope being built in South Africa and Australia, will be the most sensitive radio observatory in the world, able to detect faint signals from the early universe, study the formation of the first galaxies, search for radio emissions from exoplanet magnetospheres. And the Habitable Worlds Observatory, still in the planning stages, will be designed specifically to find and study Earth-like planets, searching for signs of life, answering the question that's driven astronomy for centuries. Are we alone? These telescopes will build on Webb's legacy, using the techniques and technologies proven by Webb, tackling the questions Webb has opened up. And they'll face challenges of their own, technical hurdles, budget constraints, political obstacles. But they'll get built, eventually, because that's what we do. We explore, we build tools to extend our senses, to see further, to understand more deeply, and every generation builds on the work of the previous one, standing on the shoulders of giants, pushing the boundaries of knowledge a little further. Webb is one of those giants, a milestone in the history of astronomy, a telescope that will be remembered for generations, not just for what it found, but for what it made possible. And it's not just about the big telescopes, the flagship missions. Webb's success is inspiring a new generation of scientists, engineers, students, people who see what's possible, who want to be part of the adventure, who want to contribute to our understanding of the universe. That's the real legacy of missions like Webb, not just the data, not just the discoveries, but the inspiration, the sense of wonder, the realization that the universe is knowable, that we can figure it out, one observation at a time. And that's worth more than any single discovery, because it ensures that the work will continue, that the next generation will take up the challenge, that humanity's quest to understand the cosmos will go on. So as we look back on Webb's first 3 years, as we marvel at the galaxies it's found, the planets it's studied, the black holes it's revealed, let's also look forward. Let's think about what's coming next, what Webb will find in its next decade, what the next generation of telescopes will discover, because the universe is vast, strange, and endlessly surprising. And every time we look deeper, we see something new, something that challenges our understanding, something that makes us question what we thought we knew. That's the beauty of science. It's never finished. There's always more to learn, always deeper to go, always new mysteries to solve. And James Webb, for all its achievements, is just the beginning. It's shown us what the universe looks like when we open our eyes a little wider, when we build tools powerful enough to see what was hidden, and it's shown us that the universe rewards curiosity, that the questions we ask lead to answers that spark new questions, that the journey of discovery is endless, and that every step forward, every new observation, every surprising result brings us closer to understanding not just the universe, but our place in it. And that, more than anything, is what makes this work worth doing. Not because we'll ever have all the answers, but because the search for those answers, the process of discovery itself, is what makes us human, what drives us forward, what connects us to the cosmos and to each other in ways that transcend time and space. James Webb has given us a gift, a window into the universe's past and future, a tool for exploring the unknown. And now it's up to us to use it, to learn from it, to let it guide us toward truths we've only begun to glimpse.